Welcome to today's lesson on interpreting distance-time graphs to calculate speed. Today, we will examine distance-time graphs in detail and learn how to use them to calculate speed. So far, you have learned the formula for calculating speed and how to calculate average speed. You also know the main features of distance-time graphs, such as understanding how to read distances and times from the axes, and recognizing the significance of different slopes. Building on this foundation, we will now explore how to calculate speed from distance-time graphs. To remind you, distance-time graphs are a powerful tool in physics for visualizing and analyzing the motion of an object over time. On these graphs, the x-axis represents time, the y-axis represents distance, and the slope or gradient of the line on the graph indicates the speed of the object. A straight line on a distance-time graph indicates constant speed, while a curved line indicates changing speed. Now let's delve into specific examples to understand how to calculate speed using these graphs. Consider a distance-time graph of a person running. The graph shows that the runner starts at a lower, constant speed for the first 10 seconds and then increases their speed for the next 5 seconds. To find the speed, we need to calculate the gradient of the line during these time intervals. First, let's calculate the speed between 0 and 10 seconds. In this interval, the person runs a distance of 20 meters in 10 seconds. We use the equation speed equals change in distance over change in time. For this interval, that is 20 meters over 10 seconds, which equals 2 meters per second. Now let's calculate speed for the next interval, between 10 and 15 seconds. During this interval, the person runs a distance of 20 meters in 5 seconds. Again, we use the equation speed equals change in distance over change in time, which is 20 meters over 5 seconds, which equals 4 meters per second. By dividing the change in distance by the change in time for each segment, we can determine that the runner's speed was 2 meters per second for the first 10 seconds and increased to 4 meters per second from 10 to 15 seconds. From this example, it is clear that calculating speed from a distance-time graph involves determining the gradient of the line. This is straightforward in this case as the graph is formed of straight line segments, so we can divide distance by time. Next, let's consider a more complex scenario where the speed is not constant. Imagine a person setting off on a bicycle, and the graph shows a curving line upwards, indicating increasing speed. To find the speed at any specific point on this curve, we need to draw a tangent to the curve at that point. But what do we mean by a tangent? Recall from our maths lessons that a tangent is a straight line that touches a curve at a point but does not cross the curve. For instance, the green line in the diagram on the right is the tangent, and this touches the red curve at the point t equals 10 but does not cross it. Suppose we want to calculate the speed of the cyclist at 20 seconds. To do this, we need to draw a tangent line touching the curve at exactly the 20-second mark. Then, to find the speed, we draw a triangle using this tangent line. It doesn't matter how big or small this triangle is, as we are just using it to find the slope of the green tangent line. So in this case, let's just use the bigger triangle. We can see that the tangent indicates a change in distance of 125 meters over a change in time of 10 seconds. So we can use the formula speed equals change in distance over change in time, and substitute in 125 meters and 10 seconds to get an answer of 12.5 meters per second. So after 20 seconds, the cyclist is traveling at a speed of 12.5 meters per second. From these examples, it is clear that calculating speed from a distance-time graph involves determining the gradient of the line. For straight line segments, which represent constant speed, this is straightforward. Distance divided by time. For curves, which represent varying speed, draw a tangent at the point of interest and then calculate the gradient of this tangent. Understanding these principles allows us to interpret motion effectively and apply this knowledge to everyday situations. For instance, predicting how long a car trip will take or understanding the behavior of different moving objects both in sports and in nature. In today's lesson, we delved into the main features of distance-time graphs. We learned that the horizontal axis represents time and the vertical axis represents distance. By examining the gradient of these graphs, we can determine an object's speed. We discussed how to calculate the speed of an object when it has constant speed, which is represented by a straight line on a distance-time graph. We also looked at the more complex case of using a tangent to calculate the speed at a specific time when the speed is varying. Watch the rest of the GCSE physics course at Sophos Education.